Hey buckaroos and buckarettes, it's good to be back with you. I've got a statics problem for you today, and this one's based on a homework problem I assigned in my class. And it's we've got a cart on a ramp here. Now normally these things the cart's moving. In this case it's static. The cart is being supported horizontally on a pretty steep ramp. That's 40 degrees, so that's pretty steep. And it's being supported at a force on one end, acting at an angle theta. So the question is, find F, force, and find theta, the angle of that force, so that this cart stays horizontal. It just sits there. It's on the ramp, and it's got a roller here, a frictionless roller, so it can move up and down the ramp. We're trying to find F and theta so it just sits there. All right? So remember, the recipe for solving statics problems has 4 mandatory steps, 1 optional one. The mandatory steps are working diagram, well that's that, a free body diagram, equations of static equilibrium, and then solve for something. And then the 5th optional step is enjoy baked goods in celebration of getting the right answer, because we are not savages. All right, so let's get started here. We're going to start there. Next thing we're going to need is a free body diagram. Now remember, free body diagram. Free is the important word there. A free body diagram is that you take some part of the structure, and I'm going to take the cart there, and I'm going to cut it free, mathematically, of the rest of everything that's going on. Now if I remove the ramp, if I cut it free from the ramp, it doesn't mean the ramp's not there, it's still there. And the way the ramp communicates its presence to that cart there is the force acting perpendicular to the ramp, normal to the ramp, through that wheel. Okay, so here's what it's going to look like. So this is the working diagram. Let's draw the free body diagram. Mess that up, there we go. Okay, so here's the cart. Now by the way, I'm assuming the weight is in the middle here. This is a uniform cart, so I'm assuming that it's ½ a meter from either edge to the center of gravity. Center of gravity is in the middle in this case. So here's force, and this is called a normal force. And normal meaning perpendicular, not normal and abnormal, but normal in this case means perpendicular. And I've got the applied force there, and let's see, I've got weight there. Well, all right. This is fine. Well, it's not a free body diagram yet. Hang on. Now it's a free body diagram. You have to have positive sign convention. So I got my positive sign convention. I'm good. Now, this problem is symmetric. It wouldn't be too surprising if F and Fn were the same, and that the angle from horizontal to there and horizontal to there were also the same. It wouldn't be surprising. Is it true? I don't know. Let's use the math to find out. It's okay to use your intuition to try to anticipate an answer, but it's not okay to use your intuition to replace calculation. That's how you drop bridges in the water. That's how you tip cranes over. Bad things happen when you do too much of that. So let's do this. Now, if I'm going to sum the forces in the horizontal and vertical direction, it would be great if they were actually in the horizontal and vertical directions, wouldn't it? So let's fix that. Now, let's define this as theta. We don't know what that is. That's given. So here's the components, F in the y direction and F in the x direction. Now, let's also define Fn in the x and y directions. And this is going to get a little busy here. I'll clean this up in a second, but let's put all the pieces on here first. Now, double subscripts, not a huge fan, but I don't know what else to do right here. So let's leave that. Now, I don't need that hypotenuse anymore. I've got the components. So I'm going to go ahead and erase that. If I find my eraser, there we go. Now, when we want to know theta, we can use a little bit of trig to figure that out. Now, 40 degrees from the horizontal is the angle on the ramp. So which one of these is, I guess it's called alpha here, which one of those is alpha? I think it's this one. I think it's that one, but let's double check. Now, physics doesn't know or care anything about our coordinate system. Our coordinate system is arbitrary. We can make that anything we want. Okay? It's just there for the bookkeeping, for the analysis. Physics does know what horizontal and vertical are. Those are aligned with gravity. So gravity goes down, that's vertical. Anything perpendicular to that is horizontal. So physics does know what horizontal and vertical are. So let's start here. There's horizontal, and there's vertical. Now, my ramp is rotated from the horizontal by 40 degrees. Well, if the horizontal is rotated, the vertical must be rotated too. And I don't know, from geometry, I guess, and I had it in 10th grade, but there we go. There's 40 degrees, so that must be alpha right there. Okay? Based on this, that must be alpha, because that angle there and that angle there are the same. So with that, I'm going to clean this drawing up a little more. Now we know alpha is 40 degrees. So this, by the way, this looks a lot cleaner now, doesn't it? Well, it will in a second here, hang on. There. That looks a lot cleaner. So now with all the diagonal forces broken into their horizontal and vertical components, let's start writing equations of motion. That's step 3 in the process. Summations in the x direction. Now I've got a problem here. If I write summations in the x direction, that looks like that. Do I really want the same variable to mean two different things in the same equation? That's bad. So I'm going to fix this. I'm going to call this horizontal, right? To distinguish it from that. F of x is something we're solving for, but this is the sum of the forces in the horizontal direction. It's really bad to write ambiguous equations. Don't do that. Okay, so there's the forces in the horizontal direction, some of the forces in the vertical direction. Okay, there's some of the forces in the vertical direction. And the last thing I need is I need to sum the moments about some point. It doesn't really matter what. I don't really care what n is. I mean, I have to figure it out anyway. Pick a point. Sure, let's pick this one. And I'll call that point, I can't call it n. I already used n for something else. How about if I call that point there A and that point over there B? I just need to give them a name that's not ambiguous. So I'm going to sum the moments about point B, and that circle there means it's a point, okay? All right, let's see. Let's just start going through the forces here and writing down the associated moments. F of x goes right through point B, so F of x does not create a moment, so I got that one taken care of. Fy does create a moment, so that's 1 meter times Fy. So far, so good. Now, is it positive or negative? Well, about that point, Fy tries to rotate the box clockwise. Well, I've decided counterclockwise is positive, so this has to be a negative moment here. About this point, W tries to rotate the box counterclockwise, which I've decided is positive. So 0.5 meters times W, and that all equals 0. All right, let's write down some other stuff here. Let's see. W, I'll get out of your way here in a second, is 9. Okay, W is 9.81 meters per second squared times 100 kilograms, so it's 981 newtons. So we know what that is. Let's see, how about the normal forces here? I know that, let's see, let's draw a force triangle. I'm starting to run out of real estate on my little board here. I'm going to go over here just because that's where the room is. And what I want to do here is I want to draw this normal force goes up through there, my F normal, perpendicular to the ramp, because this wheel can't make any forces parallel to the ramp. Let's just draw a quick force triangle and make sure we know what we're doing here. There's alpha, there's F normal, and pointing in that direction. So there's F normal Y, and F normal in the x direction. With that, let's see, how far down can I go? Right there. Ooh, we'll fit this in. Okay, so there's normal forces in the x and the y, the components of the normal forces in the x and y direction, written as Fn and alpha. So what this means is Fnx and Fny aren't two variables. They're related. So let's, I'm going to erase all this, and I'm going to break this down into x and y, or redefine the x and y components, expand the x and y components, and then we'll solve, okay? So let me get rid of this and get rid of all this stuff. Okay, so let's see. Fx, I really don't know what Fx is. So there's Fn, and that's going to be sine alpha. So there's one equation. Next equation. Okay, there's my next equation. And my last equation here. Okay, because W is 981, half of that is 490.5. There's that half right there. So Fy equals that. So I've already solved for one of them. Now if I solve for the rest of these, I'm going to write this down here. I got my little cheat card here. I want to make sure I write these down correctly. I get f of x is 411.578 newtons, and Fy, get out of your way here in a second. I've seen one of those numbers before. I wonder what this means. Well, let me, I'm going to erase right here again to make some room on my little board. If I figure out, let's see, let's draw this force triangle. There's F, and there's theta. That's a perpendicular right there. If I work this out, Fx over Fy is tangent theta. Well, you solve that, and you get theta equals 40 degrees. And if you use the Pythagorean theorem, you wind up with 640.302 newtons. Right, so there we go. Started with working diagram, free body diagram, equations of static equilibrium, and we solved for something. So we're there. Celebration, time for some baked goods. I hope this helps, and we'll talk to you next time.